Hello everybody. In this video we're going to discuss the one of the very famous laws that relate to fluid statics, which is called Pascal's law. Um, I'll first read the law, and then I'll give an example to make it clear what we mean by this law. So the law states that the pressure applied to a confined incompressible fluid increases the pressure throughout by the same amount. There are a couple of words that I want to discuss before I go into the example. First, the word incompressible fluid. Incompressible fluid means that the volume of the fluid and accordingly the density don't change with pressure. So the fluid will have the same volume even if the pressure increases. So this is mainly for liquids. For gases are compressible. If you have a gas and you can compress the gas, you can apply pressure to decrease the volume of the gas without leaking. But in case of liquids, it's almost impossible because they are incompressible. The second word is confined. Means that the fluid is kept in a place where there is no way for the fluid to escape. So it's confined in a place. So let's like see the example, and I think this will make the law much easier to understand. So we will compare two cases. The first case is a container that has a U shape, and this container has two sides that are open to the atmosphere. The areas of these two sides are equal, so A1 equals A2, and of course the fluid is filling the whole container. It's not the whole container, I mean the filling part of the container, and this is a connected fluid. The surfaces are both exposed to the atmosphere, so pressure P1 and P2 are equal, which is atmospheric pressure, and similarly P3 and P4 are at the same height in the same connected fluid, so they have the same pressure. So this is a very simple case. So I don't think there is any problem with this case. Now we will add one more modification to this case, which is case 2. So for case 2 we have the same thing, the same container with the same areas, but we have something new here, which is that we have two pistons in the two sides. The piston is kind of it's closing the container. It means that the liquid cannot escape from the sides between the container and the piston. And one of the pistons is exposed to force that leads to a pressure P1. So there is a pressure that is applied to the piston to the left, while the piston to the right has no pressure applied to it. So now what we are going to, or the question that we want to answer here is that will the applied pressure that is applied only here will affect the cylinder to the left only, or it's going to affect both? So you might think that, okay, this is a pressure that's applied to this side, so the pressure P1 is going to be higher than P2 because P2 is not exposed to this pressure, and P3 is higher than P4 because P3 is exposed to the pressure while P4 is on the other side. This is what you might think. This is correct in case of solids. Let's think of a table, for example, and you are applying a lot of pressure on one side of the table and the other side is not exposed to this pressure, so the side that's exposed to the pressure is the one that will be affected, while the other side is not. But in case of liquids, this is a different case, and this is what Pascal's law is about. So it says that the pressure applied to a confined incompressible fluid, so this is a confined incompressible fluid, it increases the pressure throughout, meaning that it increases the pressure in the whole fluid by the same amount. So if you look again here to this example, we will see that based on Pascal's law, the pressure that's applied here is not only affecting this side, it affects all the fluid. So it means that the pressure P2 is going to increase as well. And still the fluid static laws that we mentioned before still apply. So P1 is still equal to P2 and P3 is still equal to P4. But the new P1 is higher than the old P1. I mean, this P1 is higher than this P1. But P1 and P2 here are equal to each other, and P1 and P2 here are equal to each other. These are higher in value, but these two are equal. And the same for P3 and P4. So, yeah, and I hope this example clarified the point. Now, there is one very interesting thing about Pascal's law, which makes it very, very useful, is that we can do one more modification to case 2. So we can change the case by increasing or making the areas different. So I will make A1 smaller than A2. Okay. That's still Pascal law applies, and we can apply P1 to the piston to the left. And of course, there will be the result of this is that there is some pressure on the other piston in the other direction. Okay, so now we can apply the same equation or apply the same concept that P1 is equal to P2 because Pascal law states that. And since P1 equals P2, we know that the pressure is the force over area. So force 1, which is force on this piston, over area 1, which is this area, is equal to the force on this piston over area 2, which is the area of the second piston. We can rearrange the equation to put the forces, ratio of the forces on one side and ratios of the areas on the other side. So we can say that F2 over F1 equals A2 over A1. It means that the force that this piston is applying upward divided by the force that is applied on this piston is equal to this area over this area. So since area 2 is larger than area 1, then F2 is larger than F1. This means that and again, please keep in mind that the Pascal law and all the laws that we mentioned about the points at the same elevation for a fluid are all for the pressure, not for the force. The equal quantity is the pressure, not the force. And this is why we can, by this small tweak in the design of this system, we can make something very useful. So we make use of the equal pressure. So the pressure here is equal to the pressure here, but we change the area, so the forces will change. So it means that we can apply small force here, a very, very small force here, and this force will lead to big pressure, because small force over small area will lead to big pressure, and this big pressure here will lead to a big force here because of the big area. So this is a very interesting thing. Okay, so you can put small force on the small piston to generate large force on the large piston, and this is something that we use a lot in our daily life. There are a lot of gadgets and a lot of tools that we use that depend on this in this concept. One is the jack that we use to lift the cars, for example. You know, a car can be as heavy as 1 ton, for example, and with small push-ups that you can push for this handle, you can raise the car upward. Okay, so the amount of force that we are applying here is very, very small, but this is the small area and this is the large area. So the small force that we are applying here is leading to a lot of force that comes out on the other side that is high enough to lift the car. And the same for the lifts that workers use to lift them upward to high elevations, or the lifts that can lift heavier vehicles like trucks or heavier cars. So these are all hydraulic lifts, and they are all based on Pascal's law. So this is a very, very interesting thing. Now we'll just have one example to solve here, and just to practice this concept more. We have a hydraulic jack that is used in a car repair shop, in the figure here, and in the piston has an area of the pistons have area of 0.8 centimeter square, and pay attention to the units. It's 0.8 centimeter square, which is the small area, and 0.04 meter square, which is the large area. And there is a hydraulic oil here that has specific gravity of 0.87, and it's pumped in as the small piston on the left side is pushed up and down. So this hydraulic lift is filling the whole um, volume between of the jack. So it raises the large piston on the right side, so there is small force that's applied here to raise this piston on the right. We have a car that weighs 13,000 newtons. This is the weight of the car. It's not the mass, it's the weight, which is m times g. So it's already a force. So you know the force that is applied by the car is 13,000 newtons, and we want to push this car up. So in the beginning, when both pistons are at the same elevation, so in the beginning we want to push the car upward, and in the first state this piston and this piston are at the same elevation, and we want to calculate the force F1 that we need to have so that the piston can carry or hold the weight of the car. So we need the force that is needed to apply here so that the force on the other side is enough to lift the car, which is 13,000 newtons. So this is going to be a very, very simple thing. We are going to apply the same concept that we applied before, but first we have to unify the units. So and this is a very important thing. And if you remember at the beginning of the course, I said that the units are very, very, very important in this in fluid mechanics. So the area 1 is 0.8 centimeter square, which is 8 times 10 power minus 5 meters square. A2 is 0.04 meters square. And the specific gravity is 0.87, which means that the density is at 170 kilograms per meter cube. The force F2 is 13,000 newtons. So what we are going to do is a very simple thing. We are going to say that the pressure here at this piston and at this piston are equal. So F1 over A1 equals F2 over A2. And we know that we know F2, A2, and A1. So we can substitute to get the value of F1. So it's 26 newtons. And this is a very, very interesting thing. And if you think of the numbers, this is an amazing thing. You can apply a force of 26 newtons, only 26 newtons. It's a very, very small force that will generate force that is strong enough to lift a car that is 13,000 newtons. So it's a lot of force that is generated from this, 500 times the force that you exert on the small area. So this is the first thing. The second case is similar, but instead of having the two pistons at the same height, we will have a height difference of 2 meters. So what we are going to do is the same. So we are going to apply the same law, and we have to apply to 2 points at the same elevation. So it's going to be applied to this point and this point. So at this point the pressure is F1 over A1. Okay, so we don't know F1, but we know A1. And at this point, we know that the force, the pressure is going to be the pressure by the car and the head of this hydraulic fluid. Okay, so this is the only difference between this case and the previous. That P2 is F2 over A2 plus rho GH, which is the pressure due to the height of the hydraulic fluid on this side. We know the force, we know the area, we know the density, you know G, we know the height, so we know everything. So we can calculate the pressure at point 2, which is equal to the pressure at point 1. So we can say that the force is the pressure times the area, and by this we can find that the force is 27.4 newtons. So this is a very interesting thing. You can see these 2 meters are just increasing the force by 27.4 newtons. And the interesting thing also is that you just apply the concept to any 2 points at the same elevation. It doesn't have to be 2 pistons at the same height. You can apply to any 2 points at the same elevation. You can even apply it to the point here and point here. There will be some common height here that will cancel out, but at the end of the day, it's the same concept that you can apply to any 2 points. So this is the end of the example, and next time we will discuss one other interesting application, which is the hydrometer or the pressure measuring devices in general. So I'll see you then, John. Goodbye.